Assalamualaikum and good day to all students. This is the slides prepared for Chapter 14, Processor Structure and Function, which is equivalent to our Module 5. We are still in the CPU unit. Previously in Module 4, we have looked into instruction set architecture, ISA. We look at the characteristic and functions and also the addressing modes. Now we are focusing on processor itself. So we're going to start with processor organization and then register organization and the rest of the CPU. This chapter discusses aspects of the processor. We begin with a summary of processor organization. So registers which form the internal memory of the processor are then analyzed. We are then in a position to discuss the instruction cycle, a description of the instruction cycle, and a common technique known as instruction pipelining complete our discussion. And this chapter concludes with a brief examination of some aspects of the x86 and ARM organizations. So let's start with 14.1, processor organization. To understand the organization of the processor, let us consider the requirements placed on the processor, the things that it must do. Let us look at one instruction example, add AEX total. So first we need to fetch the instruction. So that instruction, we got it from the memory. Then we need to interpret or decode the instruction. See what do we want to do? It says that we need to add. Then we fetch data. So the instruction sees that we have to get the data total from the memory. And then we process the data. So we have to do some addition by ALU. And lastly, we write the data because once we add, we need to save it in AEX register. To do these things, it should be clear that the processor needs to store some data temporarily. It must remember the location of the last instruction so that it can know where to get the next instruction. It needs to store instructions and data temporarily while an instruction is being executed. In other words, the processor needs a small internal memory, which is the register. Figure 14.1 is a simplified view of a processor, indicating its connection to the rest of the system via the system bus. Students will recall that the major components of the processor are arithmetic logic unit and also control unit. The ALU does the actual computation or processing of data, while the control unit controls the movement of data and instruction into and out of the processor and controls the operation of the ALU. In addition, the figure also shows a minimal internal memory consisting of a set of storage locations called registers. Figure 14.2 is a slightly more detailed view of the processor. The data transfer and logic control path are indicated, including an element labeled internal CPU bus. This element is needed to transfer data between the various registers and the ALU because the ALU in fact operates only on data in the internal processor memory. The figure also shows typical basic element of the ALU. Note the similarity between the internal structure of the computer as a whole and the internal structure of the CPU. In both cases, there is a small collection of major elements. Remember the components in the computer, we have processor, I/O, memory, and the bus in the middle. So inside the processor, we have control unit, ALU, and also registers. Both are connected by data path. Now we are going to look at the computer external system bus. Just like the bus we use in our everyday life to transport passenger between one place to another, a bus in a computer is used to transport bit from one component to another component in the computer. So we have CPU component, main memory component, and also I/O subsystem. So we have three different buses. So we have address bus to transport again from the component, and if you want to use transfer data only, you use data bus, and for control elements you use control bus. So when we say our system bus width is 32-bit, it means it has 32 lines to carry, and each line can carry 1 bit. So look at this example. The analogy that I can give you is if we have a bus with 32 seats and we need to transport 64 passengers. So we can't fit into one bus. We need to use 2 buses. After the data bus, the next set of bus is control bus. Its job is to determine the direction of the flow from which component to which component, and also to make sure that the data doesn't collide with each other. So the third bus is the address bus. So if you want to know the location of the source of the destination, so we need to send the address in the address bus. How are you guys holding up? Masih okay? Tak okay? Sabar na? Okay, let's continue. Next, we move on to 14.2 register organization. As discussed before, a computer system employs a memory hierarchy. At higher levels of the hierarchy, memory is faster, smaller, and more expensive per bit. So we see a reference to digital logic. So our register can be implemented using D flip-flops. The registers in the processor can perform one of these two roles, as a user visible register or a control and status registers. There is not a clean separation of registers into these two categories. For example, on some machines, the program counter is user visible, example our x86, but on many, it is not. But for discussion purposes in this chapter, we will use these two categories. So this slide will further explain about user visible registers. There are 4 categories: general purpose, data, address, and condition codes. For general purpose register, sometimes they are used within the instruction set is orthogonal to the operation. That is, any general purpose register can contain the operand for any opcode. This provides true general purpose register use. Often, however, there are restrictions. For example, there may be dedicated registers for floating point and stack operation. So example of general purpose register may be EAX, EBX, ECX, EBX. In some cases, general-purpose registers can be used for addressing functions. Example, register indirect or displacement. In other cases, there is partial or clean separation between data registers and address registers. Let's look further into address register. So the three examples given, for segment pointers, in a machine with segmented addressing, a segment register holds the address of the base of the segment. There may be multiple registers, for example, one for the operating system and one for the current process. As for index registers, these are used for index addressing and may be auto-indexed. And for the last example, stack pointer, if there is user-visible stack addressing, then typically there is a dedicated register that points to the top of the stack. So this allows implicit addressing, that is, push, pop, and other stack instructions need not contain an explicit stack operand. And our final category, condition codes. They are at least partially visible to the users. Next slide will further explain it. For example, an arithmetic operations may produce a positive, negative, zero, or overflow result, in addition to the result itself being stored in a register or memory. A condition code is also set. So, is the result zero? Is there an overflow? What is the parity flag? So all of these is set into condition code. The code may subsequently be tested as part of a conditional branch operation. So these condition code bits that we collect will be put into one or more registers. Usually they form part of a control register. Generally, machine instructions allow these bits to be read by implicit reference. So we can know whether the result is zero, overflow, and so on. However, bear in mind, as a programmer, we cannot alter them. The result is fixed. The condition code change when our answer change. However, for your information, many processors, including Intel and MIPS processors, actually they don't use condition codes at all. Rather, conditional branch instructions specify a comparison to be made and act on the result of the comparison without storing a condition code. Table 14.1 lists the key advantages and disadvantages of condition codes. We are currently looking at the roles of the registers in the processor. So we have looked at the first role, user visible register, and now we're going to look at the second role, control and status registers. It is the opposite of user visible, which means that these registers, the control and status, are not visible to the user. Some of them may be visible, but to machine instructions executed in a control or operating system mode. They are employed to control the operation of the processor. Of course, different machines will have different register organizations and use different terminology. So you might see different acronym used. In this slide, we list a reasonably complete list of register types, and I will explain briefly the description. The four registers which are essential to instruction execution are first, the program counter, which contains the address of an instruction to be fetched. So after we have the address of the instruction, we have the instruction register, which contains the instruction most recently fetched based on the address. So if PC and IR are for the instructions, we are going to look next to the one for data. MAR, Memory Address Register, contains the address of a location in memory, while Memory Buffer Register contains the word of data to be written to memory or the word most recently read. So this is how it typically works. The processor updates the PC after each instruction fetch, so that the PC always points to the next instruction to be executed. A branch or skip instruction will also modify the contents of the PC. The fetch instruction is loaded into an IR where the opcode and operand specifiers are analyzed. Data are exchanged with memory using the MAR and MBR. Remember the three categories of buses? So in a bus organized system, the MAR, because it's address, will connect directly to the address bus, while memory buffer register, which contains data, will use the data bus. User visible registers in turn exchange data with the MBR. The four registers just mentioned are used for the movement of data between the processor and memory. Within the processor, data must be presented to the ALU for processing. The ALU may have direct access to the MBR and user visible registers. Next, we are going to look at flags. Many processor designs include a register or set of registers, often known as Program Status Word (PSW), that contains status information. So this is not actually the result, but the status. Whether overflow happens, whether the result is 0, whether interrupt happens. So the PSW typically contains condition code plus other status information. In the next slide, it will explain more the role of these flags. This slide explains the flags affected by arithmetic operation, such as zero, sign, carry, overflow, auxiliary carry, and parity flag. Let's look at one example. We have two numbers, 06 plus 654 hexa. We convert these two numbers into binary numbers. So one hexa digit is equivalent to 4 binary digit, and we do the normal addition. So from the LSB, from right, we add, so 0, 0, follow me, 0, 0 equals to 0, 1 plus 0 is 1, 1 plus 1 is 0, and we have 1 carry up there, and 1 plus 0 is 1. And please continue until the end. Now we have our result, so we are going to set our flags. Now, carry flag is set when the result is too big or too small for the operand. We have 8 bits and the result is enough because the result is only 7 bits. So we don't have to set carry flag, means carry flag is 0. Then we look at sign flag. So sign flag is the MSB here, so the last bit, and it is 0, so our sign flag is 0. If it is 1, then our negative, then we set 1. But now it is positive 0. So what is auxiliary carry? So auxiliary carry, so if we have 8 bits, it is the carry between bit 3 to bit 4. Since 1 plus 0 is 1, we don't have a carry up there. That means our carry is 0. No carry here. So our auxiliary carry is 0. Next, parity flag. We are using even parity. So how many 1 there? 1, 2, 3, 4. So 4 is even. So our parity flag is even is 1. Odd is 0. Our result is not 0. So our 0 flag is not set. Not set means 0. Set means 1. Overflow is basically like carry flag. The difference is that carry flag is for unsigned and overflow is for signed. And there is no overflow here, so overflow is 0. So this result is the condition code that we set in our flag registers depending on our result here. So we do the addition first, we get the result, and from the result we look which condition is set and we set it inside the flag registers. Now students can try with example 2. Another example, example 3. Try this. If you have questions, you can ask in our Telegram classroom. As you can see here, our condition code in our flag registers are different depending on the size of our operand. So if we are using word size, then we have a different overflow. So sorry, our overflow is okay. Which one is different? Our sign flag will be different compared to if we use the word. So why don't you try this in your assembly language, and as usual, step over and see the results. One last example, but here we have a negative number, so please change it to 2's complement first and then do addition, and based on the result you can set the condition code in the register flags. In this slide, we are going to look at two 16-bit microprocessors that are designed at about the same time. So we want to compare between Motorola MC68000 and also Intel 8086. Motorola partitions its 32-bit registers into 8 data registers and 9 address registers. It also includes 32-bit program counter and 16-bit status registers. The Motorola team wanted a very regular instruction set with no special purpose registers, different from Intel, because they are more concerned with code efficiency. So they want code efficiency, which led them to divide the registers into 2 functional components. So it is a rather reasonable compromise. Meanwhile, Intel takes a different approach than Motorola. So every register in Intel is special purpose, although some are also usable as general purpose. So we know AX, BX, CX, and DX as data registers, but they can also be used as general purpose in some instruction. For example, a multiply instruction always uses the accumulator in AX. Like Motorola, Intel also includes an instruction pointer and also a set of 1-bit status and control flags. So the point we're trying to make is that the comparison should be clear to the students. There are no universally accepted philosophy concerning what is the best way to organize processor register. It is actually a matter of judgment and taste. Which one weighs more for you? You want a general purpose, you want generality, you want the code to be compact. It's really up to the designer. The next slides will explain more on these design issues. Again, there is no clear best design approach. It is really up to the designer. You can follow the Motorola way or you can follow the Intel way. This slide looks at the design issue of what is the best number of registers perfect for each CPU. Generally, more registers, yes, you can have more operands, but you have the trade-off is you have a reduced memory bandwidth. Next, and the last one is the design issue of the register length. We know that the register should be wide enough to hold the longest address. And also the data registers can hold most data types. However, as explained in class before, the registers are not wide enough to hold the memory, so that's why we have indirect memory register type of addressing. And also, we can combine the registers to store a longer format. If you remember in lab 2, we explained about the multiply instruction. So usually the result of the multiply instruction is double the amount. So instead of just using dx, we combine it with ax. So half part is in dx, the other half part of the answer is in ax. This is the end of part 1 of chapter 14, module 5, processor. You should be able to distinguish between user visible and control status register and discuss the purpose of registers in each category. You also know about the buses and how to design. What is the trade-off? Next, we're going to move to 14.3 instruction cycle in the next video.